A most wonderful good afternoon, ladies and gentlemen. We are now in week 21. That means after this session today, we've got only 3 more sessions together. Don't cry, because you're most likely not going to see me next year, because I only teach first-year students, so you get rid of me. You made all the right noises. Thank you. The plan for the next 4 sessions, so that includes today, is for the main subjects that we discussed, I will do brief revisions about the things that you need to know for the upcoming exams. Now, I had a look again at the exam paper for Bi308, and just to let you know the format of that paper, it will be exactly as it was last year. That means you have 2 hours to answer 2 sections. Section A is 30 multiple choice questions, and these multiple choice questions will cover all the topics, including health and safety, that we discussed in this module. People who know me know that one of my particular traits is that I'm a very lazy person. Which means that some of the questions from the quizzes, from the online quizzes, might turn up again in the exam paper. So if you can answer the online quizzes, you should be all right with the exam paper. So that's section A. Section B will be 3 problem questions, of which you have to answer only 1. So you can basically choose. And it will be very similar to the question that you did in the in-class test. That means a question will cover at least 2 different topics. So, for example, there might be some molecularity question plus some statistic question or something like that. Yeah. So this is what you need to focus on. Basically, all the topics. And I want to revise these things in sort of almost a reverse chronological order. That's why I think we might want to do a kinetics revision today. So this is the stuff that you really need to be familiar with. Okay? Any questions? Wonderful. So in the first place, we started with the kinetics, where we basically said we are looking at rates. And we formulated a general rate equation where we said rate, which can also be, well, we started with a reaction where A is converted into something, and A in this case is the reactant. It can be a substrate, it can be a chemical compound, it can be a population, whatever you want. So we said the rate for the disappearance of this reactant A, so rate A equals, because it is a disappearance, we have a negative sign, minus K times A to the power of M. We call this the rate constant. And this one here is the rate order. And we also said that instead of rate A, we can write the change in concentration of A over dt over the change in time. That's basically exactly the same thing. Okay? We said that the negative sign is here to indicate that it is a consumption. M, the rate order, can be any number. It can be positive, it can be negative, it can be zero, it can be a whole number, it can be a fraction, it can be an irrational number, it can be any number. So M, everything is positive. K, the rate constant, can only be a positive number or zero. What would happen if K was zero? What would happen to the rate? What do you think? Rate equals concentration, is that right?
If the rate constant is zero.
Is that right?
No, there'll be no rate.
Well, the rate, there would be a rate, but the rate would be zero, right? So, which basically means there is no change in A and nothing happens to A. So, zero is allowed, 0.1 something units, it's allowed. -5 for the rate constant is not allowed because that's a negative number. Yeah? So if you find K is something negative, question it. That's my advice. If we want to find out our rate order, what we simply can do is we can say we just use the term speed, because we know that speed doesn't have any direction. We can say speed equals k times a to the power of m. With the speed, basically, we get rid of this negative sign. And in order to find m, we just simply take both sides log, and we get log speed or rate equals m log a plus log k. Right? And this gives us basically the equation for a straight line. Y equals mx plus c. So here we would plot log rate versus log a. And we would get something like that. This intersect here would be log k. And the gradient of this thing would be m, the rate order. So it could very well be that you will be confronted with something along the line of a table where you have concentration of A and the corresponding rate. Yeah? And the question would be then, find out the rate order of this reaction. So find out rate order. And all you need to do is you calculate log A and you calculate log rate. Get your data, do a nice graph like that, and from the gradient you just read off the rate order. And you can also very easily read off your log K. Yeah? Don't forget it is log K, that means it can be negative. You can convert log K into K. So K equals 10 to the power of log K. Okay, does that make sense? So you could be asked, find out the rate order for a particular experimental data set, and you would get A and rate, and as soon as you see that, you know that you have to log both. Log A, log rate. Okay? Happy with that? We made the differentiation between M, the rate order of a reaction, and the molecularity of a reaction. And just as a sort of a quick revision, M can be any number. As I said, it can be a fraction, it can be positive, negative, because M is only a mathematical expression. The molecularity of a reaction is defined as how many atoms or ions or molecules or whatever, how many atoms actually have to collide at the same time to make this reaction go. Collide at the same time. And therefore we said M can in reality, no, the molecularity in reality can only be either 1 or 2. We cannot have a molecularity of 0. If the molecularity of a reaction was 0, this would indicate that nothing happens. So it's pretty pointless to look at that. As I said in the relevant lecture, I think there is one reaction where there is molecularity 3, but that is such a weird reaction that I will certainly not ask you that. So molecularity can be only 1 or 2. The rate order can be any number, positive, negative, 0, whatever you want, fractions, and so on and so forth. Okay? Happy with that? We then also discussed special cases of rates. And we said that in the case of m equals 0, we have basically, if a disappears, we have dA over dt, that's our rate, equals minus k times a to the power of 0, and that gives us 1. So in this case, our rate would be negative k. That means our rate is absolutely constant. We said we can represent this if we plot A versus time, and we would get probably something like that. That's our A initial here. And would go down like that at a constant pace. And once we've reached 0, it just simply would stay 0. And the equation for that, for a 0 order reaction, is A final minus A initial. These are always the concentrations, equals minus K times T final minus T initial. That's the equation. And I'm not giving you these equations in the exams, because I think you are perfectly capable of learning a handful of equations. And what you can do is actually the gradient of this gives you minus K. This approach doesn't tell you a lot about, or does not need to tell you anything about the rate order, because you know that it is a 0 order reaction. And you also know that if you plot the concentration of A versus time, if you plot that and you get a straight line, it means it must be a 0 order reaction. So when A versus time equals straight line, it must be 0 order. So you could have data where you have time and the concentration of A like that. And the question could be, show graphically that this is a zero order reaction. So all you need to do in this case is plot concentration A versus time, get a straight line, and from that your argument would be when A versus time is a straight line, it must be a zero order reaction. We can also say for the units of K, this would be usually the same as the rate. So very often it would be concentration per time. So for example, millimolar per minute. Okay, happy with that? You can't, for a zero order reaction, the concept of a half-life is meaningless. Now, if we have m equals 1, so we have a first order reaction, we would have dA over dt equals minus k times a to the power of 1. That is our general rate equation. And the corresponding equation for that would be ln A final over A initial, the concentrations, equals minus k times T final minus T initial. Or, if you don't like the ln, sometimes it's useful to have it in that form. Sometimes it's useful to have it in the version where you don't have an L, where you get rid of the ln. So this would be A final equals A initial times e to the power of minus k times T final minus T initial. So these two equations are absolutely equivalent, and you can and should use the equation that is more convenient for the problem that you've been confronted with. Now, what you might be, a question could be, for example, you see time, data, and A data. And it could very well be that it says demonstrate graphically that this is a first order reaction. So what you now need to do is you have to convert the A into lna, and with that you simply plot time versus lna and you get a straight line. Please note that in this case, the line can go into the negative of the graph because you're not looking at a negative concentration, you're looking at a negative of ln of the concentration. So that's perfectly acceptable. And again, the gradient of this gives you minus k. So if you plot ln A versus time, and it gives a straight line, you know it must be a first order reaction. So that would be your argument. Please, when it says demonstrate graphically that it is a first order reaction, please do me a favor, don't fuff around and do the graph for a zero order reaction, because A, you only lose time, and B, you already know it's a first order. Yeah? So just focus on ln versus time, not anything else. Okay? Happy with that? In terms of units, for K, the unit for K is always 1 over time. So there's no concentration in it. For example, it would be 1 over minute, which of course is the same as minute to the minus 1. Or in other words, if you are given a rate constant with the unit of minute to the minus 1, you by default know that it must be a first order reaction. Very simple. All these things are really connected with each other. A first order reaction is the only kind of reaction where a half-life actually makes sense. And we said for the half-life, this is defined as ln2 divided by k. It's the same as 0.693 divided by k. So if you have a half-life, you can very easily convert that into a rate constant. If you've got a rate constant, you can very easily convert it into a half-life. Okay? Happy with that? Can do it? Pretty straightforward. We haven't done that in the lecture, so I'm not going to expect you to know that. Just in case you are curious, if we have the reaction A plus A gives something, we would have change in A per time equals minus k times A to the power of what? What do you think? So we had m, first was 0, then we had 1. What could that be? Loud? 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 Shout it. 2. Are you shy? Oh, okay. So it would be 2. I'm not showing you the equation for that, but I show you the graph for that because it's slightly weird. And what you need to plot in this case, this is the case of, for example, you have 2 molecules dimerizing, 2 receptors dimerizing. The graph for that, if you plot time, and in this case you would plot 1 over A, and what you would see is something like that. This point here would be A initial, and the gradient of that again would be K. Just, out of interest. You don't have to learn that. I just thought, this might be one of the other reactions that as a biologist you might come across. I'm not going to ask this in the exam or in any tests, but occasionally might come across these things. Okay, are you happy with that? Yeah? Now, we also discussed the case of growth. And we said we need to actually distinguish between 2 different cases. One case we said we have A is converted into B. So, for example, if we look at a first order reaction, where we have A and time here, we get something like that for A. And for B, we would get something like that for B. And in this particular case, we noted that A at a time t plus B at the same time t is always A initial. So if you like that, if you have this and this, that's this time t. If you add them up, it always gives you A initial. Or in other words, B cannot get any larger than A initial. Let's say B at the time t, or final, whatever you want to call it, is always smaller or the same as A initial. In a case like that. Yeah? Happy with that? The second case that we discussed was when B is constantly produced and it produces itself. And we said that is the exponential growth. Which I like to abbreviate like that. So B is reproducing. And in this case, you would look at it like that. Time, and here we do B. And it would grow exponentially. And in this case, B at a certain time has no limitation in a way. B grows and grows and grows and grows. We looked at a particular case where we had a first order growth where we basically said if we have this case, we can write it as B final equals B initial times e to the power of positive, not negative. Negative is consumption. In this case, it's positive because it's growth. Positive r times t final minus t initial. And we said r in this case is our growth rate. If in an exam or something like that you call it k, that's absolutely fine with me. You can basically call it whatever you want as long as you use it consistently. Don't mix r and k's. You can call it Pink Panther if you like. Doesn't make any difference to me. Yeah? We also said that in a case of a first order growth reaction, we can actually define a doubling time. And I abbreviated that as 2/1. It's exactly the opposite as a half-life. What doesn't change is the equation, which is ln2 divided by r. So in this case, you can convert a doubling time into a growth rate or a growth rate into a doubling time, whichever way you need to do it. Are you happy with that? We also discussed the equation for logistic growth, where we have something like that. We called this the carrying capacity. But that is actually, so I probably should say logistic growth. But I'm not going to ask you anything further about the logistic growth. I just want you to appreciate that this thing exists. Does that make sense? Well, if you all got this, you should be in a very good position to do all the problem solving and multiple choice questions in the exam. Can you do it? Loud. Can you do it? Fantastic. Thank you very much. And if you've got any questions, I'm hanging around and we'll try to answer them. Thank you very much.